Okay, so general relativity. This is Einstein's theory of gravity. It describes how the geometry of space-time is distorted by mass and energy. And from these equations, the Einstein field equations, we're able to derive different geometries of black holes. I will talk a little bit more about that later, but we are able to describe different properties of black holes just from Einstein's theory of relativity. If you look, I have this diagram here that can kind of give a little more insight to what general relativity looks like. That blue grid, that's considered space-time. And we have a sun on the left side, and you can see it distorts space-time just a little bit. And then to put a little more perspective, a neutron star distorts space-time more, and then a black hole even more so. So let's talk about black holes. And what are they? Well, I have a couple images here. I have an artist's rendering of a black hole on top. If you notice, that red glowing bit is called the accretion disk. That's just some dust and particles that orbit the black hole. And then below it, we have the Event Horizon Telescope image of M87. So that can kind of visualize what black holes actually look like. But what is a black hole? Well, black holes are formed from large stars collapsing, typically through supernova. They keep collapsing to a point called the Schwarzschild radius. Once it gets below that radius, it's considered a black hole, and it becomes incredibly dense, and light itself can't even escape its pull. To kind of give a little perspective on how dense these things are, it's theorized that the smallest black hole is about the size of an atom, but has the mass of a large mountain. So it can kind of give a little insight like how dense black holes really are. But what are some properties of black holes? Well, we have the no-hair theorem. So any matter that makes up a black hole, that's totally inaccessible to us. We don't know what it was before. We just know it might have been a star, but whatever we get from the black hole is called, we get mass, charge, and angular momentum. Those are the only three properties we really get from black holes. It doesn't really matter what made up that black hole. All we know is its mass, its charge, and its angular momentum. Nothing microscopic is happening on the surface of a black hole, hence the term like no hair. And this can be seen from the different metric equations that we have. We saw earlier with Lindsay's talk, the Kerr metric, that those A's and M's were mass and angular momentum. We have the Schwarzschild metric, which is for stationary neutral black holes. And all we have is we have a couple constants here, and then we have some R's and some thetas and some phi's. Those really are just coordinates of space-time. And the only difference is this M here, which is our mass. Now, we also have a third metric that describes black holes. This is known as the Reisner-Nordstrom metric. It is really intimidating compared to what this one looks like. But all it picks up is a factor of charge. So it really kind of shows that we only have mass, charge, and angular momentum to describe these things. And if you look at this diagram here, it's a little it can give you a little insight of what's happening. You could put a chair in there, a flower, TV, mass, charge, whatever. It all goes in, but all that comes out is its mass, charge, and angular momentum. Okay, so let's take a look back at our outline. So we covered a little bit of general relativity, we covered black holes and the no-hair theorem, but now we're going to start moving slightly more quantum with it, and we'll pick up with particle pair production. So particle pair production, well, what is that? Well, in a vacuum, a pair of particles will just come into existence. And one particle will have a positive charge, and one particle will have a negative charge, energy, sorry. The one with negative energy classically isn't allowed, so they annihilate almost immediately. I have this image here that's a crude drawing of what kind of happens, but on the left side is the vacuum, and then these particles come into existence. We have a positron and an electron, and then they annihilate right away. And I also have an equation for particle pair production. This is the lifetime. So we have h bar and energy. So h bar, that's just a constant, and it's very, very, very small. So when you're dividing by something very small, it means that the lifetime itself is very short. But what does this mean for black holes? Well, that leads into Hawking radiation. Hawking radiation, if you look at this diagram over here, on the bright blue part is the space-time, and we see these particles coming into existence and annihilating. These are virtual photon pairs. These are photons that are coming into existence and then annihilating right away. But if you look at the event horizon, that's where it starts getting a little more intense here. We have the event horizon. These particles are coming to existence, but when the one with negative energy passes through the event horizon, it actually falls in to the black hole, and the one with positive energy escapes. You're adding negative energy to a black hole, but by Einstein's theory of special relativity, E equals mc squared. When you're adding negative energy, you're adding negative mass as well. So that means the black hole starts to shrink. And over time, the black hole will shrink entirely until it is nothing. And any information about that black hole is completely destroyed, and we lose what we know about black holes. So a couple other things about black holes that we get from Hawking radiation stuff. We get the temperature of a black hole. If you look, the only difference is we have mass. All the other things are just constants of nature. But mass, we have mass on the bottom and we have temperature over here. That means mass and temperature are inversely proportional. So when you add more mass to a black hole, the colder it actually gets. And then if we look at the lifetime equation, we have all these constants multiplied by a mass squared. And if you add more mass to the black hole, well, the lifetime of the black hole increases by mass squared. So I can give a little GIF here to help you visualize what's going on with Hawking radiation. We see some particles coming into existence, annihilating, and then the ones with the arrows, they will come into existence, and then the negative energy falls in, and the positive energy escapes. From those equations I showed earlier, the temperature of a black hole for a solar mass is about 60 nanokelvin. That's colder than the background temperature of the universe, which is about 2 Kelvin. And for many of you who don't know what Kelvin is, it's a temperature scale, and room temperature is about 300 Kelvin. So it goes to show how cold black holes really are, and the more mass you add, the colder they get. And then for a solar mass black hole, the lifetime of one is about 2 times 10 to the 67 years, which is very, very, very long time. So it just kind of shows that, like, as you increase the mass, the longer the black hole will be there before it evaporates entirely. And a little fun fact is that a 1 kilogram black hole would evaporate in about 0.083 femtoseconds, which is almost instantaneously. And it'll expel the energy of a large thermonuclear bomb. So it's very fascinating that just a little blip and tons of energy. So this, we talked about Hawking radiation. Now we're going to move on to, talking more about quantum mechanics. So what is quantum mechanics? Well, it's about how small particles behave in time. And as we saw earlier, information is kind of getting destroyed, but a fundamental axiom of quantum mechanics states that, different states evolve in time unitarily, which is just a fancy word for saying that information is conserved. And how is information conserved? Well, if you look at this equation here, it's very intimidating, but all you really need to get out of this equation is that information is conserved. And it's conserved through a process called normalization, which just conserves probability. And once probability is conserved, then information is conserved and everything's looking good. But how does this pertain to black holes? Well, as we saw earlier, with general relativity, information is destroyed. But with quantum mechanics, information is conserved. These are two fundamental theories in physics, and they don't agree with each other. They disagree. and it creates that paradox, hence the name black hole information paradox. And why is all this important? Well, it's to show that we really need a theory of quantum gravity to be able to unify these two theories. We have these two big theories in physics, and they just don't agree with each other. And the only way to really make them agree is to have a theory of quantum gravity. So, that's my talk.
Alex, can you do questions?
Oh, sure. Any questions?
Yeah.
So when you have that photon pair production, why is only the negative energy photons the ones that cross the event horizon? Why don't you see the positive energy photons crossing the event horizon and the black hole emitting negative energy photons?
Well, so if you were to think about it like classically, when you have I'll go back to help kind of visualize it. When you have we're only considering the case right now with negative energy falling in, but if a positive particle were to go in, well, the negative energy doesn't have enough energy to escape because we're talking about kinetic energy. And so if it has a negative kinetic energy, that will also just fall back into the black hole. And then if you were to have, so the positive particle has enough kinetic energy to escape to infinity when the negative one falls in.
Okay, thank you.
Mm-hmm.
Any other questions?
So, in the previous presentation, I described specific places where a photon can make a single rotation around a black hole.
Mm-hmm.
Is this sort of occurring there, right along the edge of the event horizon?
Yeah, it's right above the edge of the event horizon.
The photosphere is a little out from the event horizon.
Okay.
This is only important right at the event horizon.
Mm-hmm.